Let's talk about one of the hardest topics in HSC physics, the structure and function of an AC induction motor. It ties together some of the most important concepts in electromagnetism, and it feels amazing when you finally get it. Now, there are a few concepts we need to cover before we start talking about AC induction motors. Firstly, Faraday's law, which states that an EMF is produced when a current-carrying conductor experiences a change in flux. This EMF is directly proportional to the rate of change of magnetic flux. Secondly, Lenz's law, which states that when there is a complete circuit, the induced EMF will give rise to a current, which produces a magnetic field which opposes the original change in flux. I know, it's a real mouthful. Anyway, let's revise alternating current. Remember that AC current varies sinusoidally as shown here. And with that out of the way, we can actually look at the structure of an AC induction motor with this schematic diagram. First, let's introduce the stator, which is the stationary, non-rotating part of the motor. Next, the rotating part of the motor has a special name, the squirrel cage rotor, presumably because of its resemblance to a squirrel cage. And when we look at it side on, it looks like this. Side note, save this diagram for your exams. It's a great way to capture all the detail you need in the easy to draw 2D format. And the stator itself has 3 sets of opposing coils of wire. To make it super clear, here's one pair, here's another, and here is a third pair. Each set is connected to a different phase of a 3-phase AC electrical supply. This diagram on 3-phase electricity might look a bit confusing at first, but in essence, we know that AC current varies sinusoidally, and any sine wave has its peaks and its troughs. But instead of each set of coils having their peaks and troughs at the same points, they're offset by a small amount of time. And this idea is super important because it allows the stator to set up an apparently rotating external magnetic field. Yes, you heard right. The stator, i.e. the stationary part of the motor, is creating a rotating magnetic field. To understand this, consider that the vertical pair of coils are named coil 1 and are connected to phase 1 of the AC current. And to make this even easier to understand, we're going to use our right-hand solenoid rule. And we'll say that at the peak of phase 1's current, the top coil has a relative north pole and the bottom coil has a relative south pole. Then as seen in the graph, just as phase 1 starts to experience a reversal of current, coil 2 then reaches the polarity that coil 1 was just a minute ago, i.e. an effective north pole. And moments later, the north pole shifts again. So you can see how the stationary coils are creating a rotating magnetic field, all whilst having no moving parts. Now, how does all of this affect the squirrel cage rotor in the middle? As the external magnetic field rotates, the conducting bars of the squirrel cage rotor are experiencing a change in flux over time, and an EMF is induced as per Faraday's law. Now, given that the end plates of the squirrel cage rotor can also conduct electricity, it does facilitate a complete circuit between the metal bars. Now, this means that the EMF does give rise to a current, which is important because it now makes Lenz's law all the more relevant. Recall that Lenz's law states that the induced current always induces a magnetic field to oppose the original change in flux. Now, given that the rotation of this external magnetic field is what causes the change in flux in the first place, it would make sense that the direction that the current flows is one which allows it to experience some sort of force to effectively chase the rotating magnetic field, minimizing its change in flux. So there you have it. That's how an AC induction motor works. Now, whilst it is advantageous to have a brushless motor which decreases friction-related wear and tear, there are 2 key disadvantages to discuss. Firstly, given that the frequency of AC current is 50 Hz, the maximum speed that the motor could ever rotate at is 50 times a second, because that's how fast the external magnetic field rotates. This, in effect, is 3,000 RPMs, or rotations per minute. This limits its use to only very specific applications. Secondly, AC induction motors don't always rotate at the same speed. In fact, they vary slightly during its use. Let's talk about this now. As the squirrel cage rotor speeds up and eventually catches up to the rotating external magnetic field, the rate of change of flux experienced by the squirrel cage rotor approaches 0. This means that the EMF produced will decrease, because remember, Faraday's law requires that there is a relative change in flux for any EMF to be produced. And this means that the current and therefore torque on the rotor also decreases. So this causes the squirrel cage rotor to slow down or slip behind the rotating magnetic field until this slippage creates a relative change in flux between the external field and the rotor. And at this point, a torque can again be experienced. In reality, the slippage occurs over a minuscule time frame, so it's not noticeable to the naked eye. But it does constantly slip and may bring about an ever so slightly varying rotational speed and torque, which make it unsuitable for certain applications. A good example is a CNC milling machine, which requires a high degree of precision. Now that's a fairly comprehensive overview of AC induction motors. So feel free to save this video, like, share and subscribe, and of course, see you next time.